Good afternoon, and thank you for joining us for this final session of the day. In this presentation, I'll provide an overview of our work in developing and expanding a series of data sets of radiometric ages and isotopic traces at national scale, which we call an Isotopic Atlas of Australia. I hope you'll get a flavour for how those data sets add extra dimensions to national maps and models, particularly by adding a time dimension. And I'd like to thank the many people who have contributed to this work, both at GA and amongst our collaborators. If you've been participating in the earlier sessions of the EFTF showcase today, you'll have seen an exciting array of new national scale geoscience datasets, maps and models. As a quick reminder, these have included the AusArray survey and the seismic velocity models that come from it, the AusLAMP magnetotelluric survey, and the models of electrical conductivity through the deep levels of crust and mantle lithosphere, and the AusAEM surveys, again mapping electrical conductivity, but in this case in the upper few hundred metres of the crust. And these new national geophysical coverages add to others that keep improving, such as the national gravity and magnetics coverages shown here. And we've also heard from Phil and Alex in the previous session about new chemical and mineralogical data sets and maps. Each of these data sets provides a different and complementary view of the physical and chemical composition of our continent. And although all these maps you've been seeing today are all mapping different aspects of our national geology, they all share something in common. They are all views of our geology in its current state. Of course, mapping the current state of the continent is an obvious and important thing to do, not least because we live on the continent in its current state, and we need to find and manage the mineral, energy and groundwater resources as they are today. However, we know that our continent and its natural resources did not just appear in their current configuration overnight. Our geology as we map it today is the product of several billion years of history, and the resources on which we depend were formed episodically through that history. The search for new resources can be made more effective and efficient by understanding the timing of the many processes that have punctuated our geological history, and by using that information to focus the search in places with the right geological ingredients and in rocks of the appropriate age. In this presentation, I'll provide an overview of our efforts to provide insights into this long and episodic history of Australian geology and its mineral resource development. We've been doing this along with our collaborators by building a series of national coverages of geological ages and time-sensitive isotopic traces. These age and isotopic maps are building what we've dubbed an Isotopic Atlas of Australia. The central image here shows a stack of different age and isotopic coverages. In the same way that different geophysical coverages provide information about different physical aspects of the continent, these different isotopic maps provide different and complementary information about aspects of the geological history and chemical evolution of the continent. In 2020, we presented a vision for this Isotopic Atlas in an Exploring for the Future extended abstract, shown in the lower right of this image. Since that time, there have been developments both in the density and diversity of datasets, and perhaps most significantly in the online delivery of these datasets via the GA portal. These age and isotopic datasets are a national asset. Australian scientists have been at the forefront of international isotope geoscience for several decades. They have developed new methods and applied those methods in systematic ways. The Isotopic Atlas is an effort to maximise the value of this science excellence and put it in the hands of a wider group of users. Perhaps the most foundational coverage in the Isotopic Atlas is the National Compilation of Radiometric Ages. Geoscience Australia has an ongoing program of acquiring new geochronology, primarily via our in-house sensitive high-resolution ion microprobe instrument. And we've been delivering that data in publications and online in its full detail for over 15 years. In addition to delivering the data that we generate in-house, over the past few years we've put considerable effort into compiling radiometric ages from other published sources and delivering a national view of all available ages. This is what you see here. This is a screenshot from the Geochronology and Isotopes persona within the GA portal. There are now around 7,000 ages available here, from publications as early as the 1960s through to the present. GA has been a major player in the acquisition of this national geochronology coverage, with over 3,000 of these ages coming from GA publications. Our state survey partners and the university geoscience sector are also big and ongoing contributors here. Given the time, effort and cost that goes into sample collection, isotopic analysis, interpretation and publication of each one of these data points, this map represents at least $20 million worth of value. We're pretty confident that this is the most comprehensive geochronology coverage that's ever been publicly available for Australia. A national coverage like this puts the first order results of specialist geochronological studies directly in the hands of mineral explorers, rather than them having to trawl through the specialist literature to extract the relevant information. This coverage also provides us and others with a guide to the major data gaps and where we can have the most future impact with additional data collection. We're aware from our geochronological studies in frontier areas, including with our collaborators from MinEx CRC in National Drilling Initiative campaigns, that new geochronology from frontier areas is a key data set that draws exploration interest and activity. And having a relatively comprehensive coverage of ages compiled and classified with consistent terminology allows us to view this data in new and powerful ways as a time sequence. To illustrate this, we have recently released some thematic videos of Australia's geological history through time. What you'll see here is the geochronology dataset filtered to show only magmatic ages, that is, the ages of igneous rocks. The video plays from 3.5 billion years ago through to the present, and the results are shown against a backdrop of the national magnetic coverage, with an overlay of the major crustal boundaries. You can see the episodic history of igneous activity starting in the Pilbara and Yilgarn cratons in the west, and progressively building eastwards through the Proterozoic and then Phanerozoic. Here I want to acknowledge the work of Wanches Saktura from the University of Wollongong, who worked with us to develop these videos, and he did a great job. Viewing the data in this animated way provides a much clearer impression of the major episodes of activity, and equally emphasises relatively long periods of little or no magmatism. This has clear implications for the prospectivity of many mineral systems which involve magmatism, either directly as carriers of metals or as heat sources to drive hydrothermal fluids. But the Isotopic Atlas is not only about geochronology. In addition to ages of particular rock units in the upper crust, we can also use isotopic traces such as samarium-neodymium to image the progressive building of the mid and lower crusts. This was first done at continental scale by David Champion in 2013 via a compilation of neodymium model ages. At that time, the total data coverage included just over 2,500 points and was filtered to just over 1,600 points from felsic magmatic rocks to produce this gridded map that you see on the left-hand side. We have recently released an updated version of this samarium-neodymium dataset and map, again led by Dave Champion. The new dataset has more than doubled the data coverage. There are now approximately 8,000 data points, with almost 3,500 coming from felsic magmatic rocks and producing this updated national model age map on the right. I've highlighted a couple of regions in the red and yellow ellipses to show where the improvement in data coverage is particularly evident. For those not familiar with the concept of model age, you might be asking, what's the difference between this model age map and the ages of igneous rocks we were just looking at in the video animation? In general, most of the igneous rocks shown in our video are the result of partial melting in the relatively deep parts of the continental crust, typically at depths of say 20 kilometres or more. But another question we can ask is, how long has that deep continental crust been there before it was partially melted? Or put another way, when were the deep foundations of our continent extracted out of the Earth's mantle and added to the continental crust? This is essentially what the neodymium model ages represent. The new neodymium map has been used as an input to update the national interpretation of major crustal boundaries, first released by Korsch and Doublier in 2016, with a 2024 update led by Michael Doublier released just a couple of months ago, and shown here by the red line work. And in turn, the major crustal boundaries, as well as more local gradients in neodymium model age, have been shown to be a key predictor of the locations of multiple mineral systems, enabling predictive mineral potential models. An example is this recently released iron oxide copper-gold prospectivity map. You'll hear more about these prospectivity maps tomorrow in a presentation by Ariane Ford. The mapping of crustal growth and crustal architecture via neodymium isotopes is now being complemented by lutetium-hafnium analyses of zircon. This image is a very recent example from southeastern Australia from the work of David Mole here at GA. Here we see crystallisation ages of igneous rocks depicted by the coloured dots, and the background coloured contours show lutetium-hafnium model ages of the mid to lower crust, similar to the neodymium model ages we've seen in the previous slides. This image very nicely maps out the margin of the Proterozoic South Australian craton, shown in the purple colours, with the younger, more juvenile crust of the Tasmanides, shown in the green and yellow colours. David will talk in more detail about this work on Friday this week, including its implications for mineral systems fertility along this paleocontinental margin. In complement to the neodymium and hafnium maps we've just been looking at, lead isotopes in ores reveal systematic patterns related to the origin of mineralising fluids and the chemical composition of the rocks from which those fluids were derived. In particular, variation in lead isotope composition tracks the extent and timing of enrichment of uranium and thorium in the crust, as these are the elements that produce radiogenic lead isotopes. A national coverage of lead isotopes in ores was published in 2019 by Dave Houston and co-workers, and is shown by the image on the left here. This dataset is now available to view or download via the GA portal. As you might expect, we see a general pattern of more evolved lead isotopic signatures from ores in the older cratonic parts of Australia, shown in the brown and yellow colours, with more juvenile lead signatures shown by the green colours, mainly in the Tasmanides of eastern Australia. But there is considerable detail that can be drawn out of this dataset at more local scales. The image on the top right shows some of that detail in the Carpentaria zinc belt, straddling the Queensland-Northern Territory border, one of the richest base metal provinces in the world. In that region, Dave Houston noted that the lead-zinc deposits, shown by the light blue dots, lie along a pronounced gradient in the lead isotope map. That isotopic gradient also corresponds to the edge of older, thicker lithosphere to the west, shown in the blue colours in the lower right image, compared with thinner and younger lithosphere to the east, shown in the red colours. This relationship has subsequently been shown to hold in other sediment-hosted base metal provinces, providing a guide for future exploration. While already very useful on its own, the lead in ores dataset can be placed in more detailed context by an improved coverage of lead isotopes outside the ore systems, essentially a background lead isotope map from basement rocks. Such a map has not previously been developed in Australia at broad scale, and possibly not anywhere in the world. Over the past 3 years, we've collaborated with the research team at Curtin University and the John Delator Centre to develop a lead in basement map for southern and eastern Australia. This is largely the work of Jana Liebman at Curtin University, funded by the EFTF program, and primarily using the extensive archive of physical samples that GA holds from its geochronology programs with the state and territory surveys. The image here shows a map of the isotopic parameter mu, essentially a measure of uranium enrichment in the crust, with more enriched crust shown in yellow and green, and less enriched crust in blue. While this coverage is not yet national, it's well on the way. The Geological Survey of WA has been funding an equivalent coverage, also through the Curtin University team, which will complement the coverage shown here. And there's clear scope for future work to extend the coverage across Northern Australia to build a fully national dataset and to improve the density of data coverage. The neodymium, hafnium and lead isotope coverages that I've mentioned so far have been derived from basement rocks and have application to the timing and processes of crustal growth and to tracking the origin of ores and ore fluids. But isotopic traces can also be applied on transported surface materials. Here we see two relatively new isotopic coverages based on surface samples collected by Geoscience Australia approximately 15 years ago as part of the National Geochemical Survey of Australia, led by Patrice de Caratat. This sample archive has been used in a recent PhD study by Kandan Desem at the University of Melbourne to produce a near-national coverage of lead isotope signatures in surface sediments, seen here on the left-hand image. Similarly, on the right-hand side, we see strontium isotopic signatures from surface sediments collected in collaboration with partners at the University of Wollongong, with scope for expansion towards national scale. These isotopic signatures of surface materials can be used in a range of applications. These include tracking the origin of surface sediments, which can be a key piece of information in interpreting the subtle surface signals of buried mineral deposits. In addition to mineral exploration applications, the data can also find application in archaeology, agriculture, and even forensics. One example of an agricultural application is a relatively new project that we've been part of over the past year or so, funded by the Australian Research Data Commons, and in partnership with CSIRO and ANSTO. That project is aimed at bringing together the isotopic data holdings of CSIRO, ANSTO, and GA for use in food provenance applications, essentially to provide an evidence base for tracking the provenance of foodstuffs and the assurance about the processes and inputs used in food production. The chemical and isotopic composition of our foods is a product of the soils it was grown in, the fertilisers used to nourish it, and the surface and groundwaters taken in by those foods during their growth. In this project, GA's holdings of isotopic data from soils and groundwater are being complemented by data from water and food that is held by CSIRO and ANSTO. I don't want to finish without providing at least a very quick guide as to how to find the various data sets that I've presented today. This image is a screenshot from the GA portal. If you were tuning in to yesterday's presentations, you'd have heard more about the GA portal from Mark Webster. The URL in the bottom right will take you to the Geochronology and Isotopes persona of the GA portal. The default coverage you'll see from this URL is the radiometric age coverage as shown here. The list of layers on the left-hand side of this page also provides you access to the various isotopic coverages I've mentioned, such as neodymium, lead, strontium, etc. Clicking on any particular data point will bring up the relevant data and metadata about that point shown in the panel on the right-hand side. This also includes a link to the original published source of that data. And once you've found the data coverage you're interested in, there are various ways it can be filtered within the portal, for example, according to geographic region or rock type or interpreted geological process. And then you can download either the entire data set or a filtered subset by clicking on the About button and then the Download button as highlighted here in yellow. As you can see, the data can be downloaded in a variety of formats. So to sum up, we're very familiar with national scale geological maps and geophysical images. In some ways, the isotopic community has been behind the curve in putting our data together in similar national coverages. There are a variety of reasons for this, including the relatively labour-intensive nature of sample-by-sample analyses. However, I hope this presentation has shown that we now have sufficient data coverage to make meaningful and useful national-scale isotopic maps. And these datasets are now easily accessible in one place via the GA portal. As with the expanding portfolio of geophysical coverages at ever-increasing resolution, there is great potential to continue to grow the range and resolution of our isotopic datasets, providing extra dimensions to our understanding of the processes that have led to our current resource endowment and providing increased predictive power in our search for more of the resources that we'll need to meet future demand. I want to finish by acknowledging that the development of these national datasets would not have been possible without the combined efforts of many in the Australian geoscience community. Much of this work rests on the foundations of Australia's long history of leadership in isotope geoscience in our university sector, as well as its application in geological surveys. In particular, the development of the Isotopic Atlas would not have been possible without the GA Laboratories team, collaborations and data sharing with our state and territory geological survey colleagues, and with our university collaborators, ANU, Curtin, University of Wollongong, Uni of Melbourne and University of Alberta. We thank them all and we look forward to continuing to develop these data sets and the insights that come from them. Thank you.